Next up, circuits of the mind. We've got two rock stars in their field upstage. Coming on stage next. Justin Sanchez, who is the head of DARPA's Biological Technologies Office, and computer scientist Leslie Valiant. And Daniela Hernandez from the Wall Street Journal.
Hi, everyone. So as Simone said, we have two rock stars in neuroscience and AI. Leslie here is a professor of computer science and applied mathematics at Harvard, and his work has spanned parallel computing, computational neuroscience, and AI. And one of the fundamental questions that you have explored during your career is really understanding what the building blocks of cognition are. Justin is the director of DARPA's Biological Technologies Office, and he's worked on building brain-computer interfaces. Some of these have been used to treat patients with traumatic brain injuries and mood disorders. And one of the goals of the work, apart from treatment, is to really understand how the brain computes and learns. And so one of the questions that we wanted to explore today is, how can neuroscience inform the way that we build intelligent systems and vice versa? And I thought that we would start with Leslie and some of his theoretical work, and then Justin, if you can chime in after that.
Okay. So in the title, this word ecorhythm crept in somehow, so I should explain that. So the ecorhythm is a generic term which describes algorithms which learn, which live in an environment and learn from the environment so as to perform well in the environment. And so primary examples are supervised machine learning, what people in the room call deep learning. That's one example. Biological evolution is another. And further examples would be functionalities which we don't quite know of, but functionalities which we want to do in AI in the future, which are greater than the functionalities we have now. So just very roughly, how do we combine algorithms, biology, and everything else? So I just want to discuss Darwinian evolution for a second. So Darwinian evolution is something like random variation and then selecting the best. So if you think about it, if you just think of these words, random variation, selecting the best, and you wander around a college campus and go into various courses, so what kind of field would you find these words in? And the answer is computer science. Computer science studies random processes and selection. So Darwin's theory is really kind of computer science. It's a disembodied rule, no mention of biology or physics or chemistry or anything else. It's just a rule as we study in computer science. So Darwin was a kind of computer scientist. And if you study evolution and have machine learning at the back of your head, then you find out that in fact you can formulate biological evolution, Darwinian evolution, as a kind of machine learning, as a kind of supervised machine learning. It's extremely similar. I suppose the only slight difference is that we think of evolution as being kind of directionless, but once you put fitness as the direction, then it does become just like supervised machine learning, where there's a goal. So this has various consequences, technical ones, but a very generic one is that sort of humans have discussed this idea of nature versus nurture for a long time, trying to figure out what percentage of what we know is got by nature and nurture. But this view that the information which has got into us is got into us partly through evolution and then after birth through learning. So if these two processes are kind of one and the same, then, or very similar, then the moment of birth isn't anything very important. So the fact that we can't actually discern very well what happened before and what happened after isn't surprising. So this nature-nurture divide is a bit meaningless.
And how does that feed into your work, Justin?
Okay, so Leslie just shared with you a perspective on artificial intelligence. And at DARPA, we're very interested in artificial intelligence, but we're also interested in neuroscience and neurotechnology. And our mission is breakthrough technologies, okay? So, this agency was formed to stay way out ahead of any new technology that our country may face. And the one I'm going to share today is what a direct neural interface can do for neuroscience and artificial intelligence. And in just a moment here, I'm going to show you a video. But before I show you the video, let me just kind of outline what a direct neural interface is. So we got into doing this kind of work because we were trying to help people with traumatic brain injuries. Okay, so if you get bumped on the head, you can potentially lose the ability to form and recall memories. And we said, okay, that's a very difficult problem for which there are very few solutions. Can we develop a technology that could help you to form and recall memories? And that's what neurotechnology is. There are sensors that are placed in and on the brain. They measure what your neurons are doing. And again, this is where the artificial intelligence comes in. We have to build algorithms that can make sense of what all of those neurons in your memory system are doing, and then turn that into, I need to stimulate the brain in order to form and recall a memory. All right, so I'm going to show you this video. It's the first time we're actually showing this video. This is a person who's actually undergoing a surgery for epilepsy, and as a part of that surgery, they have electrodes placed in and on their brain. And this person's going to be doing an experiment for which they need to memorize 12 words, or 10 or 12 words, okay? And we're going to compare the performance of this person without the neural interface, so without a brain stimulation, and then with a direct brain stimulation in order to help them form and recall memory. So if we could just play the video, you can see what we're able to achieve today. Actually, you're showing a longer video here. This is some of our first work that we did in neurotechnology. This was before we started working on memory. We started in the area of movement and control. And these are people controlling robotic limbs just using their neural activity from their brain.
And I can do a fist bump if you'd like.
That's amazing.
This is a person that had a direct neural interface and can perceive the fingers that you're touching on that robotic arm. Again, directly back into their brain. And here's the memory video that I was just describing. So 12 words, no stimulation. So you see, you got through 3 of these words, and it does the old face palm, right? Very difficult to recall long lists. Now with stimulation. Got all of them. He said, I just have a good picture in my head. I could just see, all right? So again, it's a really tremendous breakthrough technology, but again, really illustrates how if you put together an artificial intelligence with a direct neural interface, there is the potential for us to start learning not only how the brain functions, but also how we should develop our next generation of artificial intelligence.
So what kinds of patterns are they recording, and how does that feed back into the software that you're building to record it and analyze it?
Yeah. So the very difficult challenge in all of this is, again, we've got to develop, again, signal processing that can, in 100 millisecond or faster time intervals, understand what those neurons in the brain are signaling, create a state of that, and then make a decision about what kind of stimulation we're actually going to give back to the brain. So Leslie was just talking about supervised learning and interacting with environments and things like that. We need to develop optimization techniques that occur in the computer to actually close the loop of this neurotechnology that I just showed you there.
So one of the things that we hear a lot about is this idea that, with deep learning, which is making all the waves now at companies like Facebook and Google and Microsoft, that these systems are really built or loosely inspired by how the brain processes information. Can you unpack that a little bit? And is that really true? Are these systems really behaving or thinking like the human brain?
It's an interesting question, right? I'll give just a few words on this. Right now, the decoding algorithms, for this application, very much tuned by hand, right? So we have the world's experts that know how to optimize these systems and know a lot about neurophysiology. But I think what the potential is for the future is maybe if we can integrate some of the processes that the brain does into our algorithms, maybe this could be more seamless and happen automatically.
Yes, I think the question you were asking whether these deep nets work like the brain. So, you know, I doubt it, but I don't think they have to. So, as long as the, you know, so we're trying to understand how the brain works, we're trying to do AI, so we're trying to understand what functionality the brain has or the artificial system has. But since the hardware is so different in the brain and the computer, there's absolutely no reason why we should even try to make the algorithm similar, as long as the, you know, we choose what functions we think are important.
And it's functionality, right? And you know, building upon that comment is we did not have to know everything about the brain in order to build these algorithms, you know, for this application here, right? You have to know enough about the functionality that's important to you in order to actually design them.
One thing that's come up in the conversations here is this idea that, you know, AI might replace humans, and so what can these systems do and what can't they? Like, what are they recording? What is still beyond the reach of the technology?
Yeah. So we're at the very, very early days of this kind of technology. Again, we're just showing what is possible. And the kinds of things that we're doing with it is very much in the domain of helping people that have been injured. So you saw some videos, people that are paralyzed, right, to move or feel again, or a person with a traumatic brain injury to remember again. They're just very basic functionalities. You know, we're very far away from having, again, this, you know, deep dialogues with these kinds of artificial systems. But, you know, there is potentially a trajectory to get there. That's part of the exciting aspect of doing this kind of work today.
So, I mean, in one of the videos, when the fist bump and then the touching of the fingers, I mean, those are really fascinating things. Like, what exactly is going on there that the person is able to feel and really maneuver like if they were, you know, controlling their own body?
Yeah. So one of the great things about the approach that we took to this is we said, can we develop neurotechnology that restores near natural function? So we want the people that are using these devices to just think of naturally controlling their arms or naturally just trying to remember something. And again, that's where the deeper understanding of neuroscience helps us to design those algorithms so that they're more seamless with your brain, right? And again, it's that aspect of coming up with symbiotic systems that are more seamless with your physiology, where I think there's the greatest potential for us to learn the most. But again, you know, we're only a handful of years into doing this. I think as we start to interact with these kinds of systems through a direct neural interface, again, we're going to learn so much about that.
So I'm sure these systems, they're big and they're bulky and they're hard to maneuver, right? But are there things that you're seeing that are coming up by startups or other technology companies that are trying to interface with the human brain in a way that's more accessible?
Yeah, great question. So at DARPA, we set vision for what the future you know, may look like, and then we reach out to the community to try to build technology again, that doesn't exist today. And in the examples that you saw here, we started off in those examples where people that were paralyzed, there's these big racks of computers that were doing all of the processing to do this. But what we're working on today is miniaturized systems that could be fully implantable in the brain or in the body, that have all of the processing power and battery and communications that one would need to actually have, again, what we call one of these closed-loop systems. So it's very interesting today as we see the miniaturization of electronics, improving, as we see our understanding of AI and neuroscience increasing. I really think that these three areas are ultimately going to merge together.
Leslie, are there areas where you see some of this already happening, like in the lab?
Well, no. What I see happening is what Justin was referring to, that one studies these fields and they're the same field. So lots of things we don't understand about the brain. So when you remember, you recall the breakfast that you had this morning. If you had breakfast, I mean, no one knows whether it's 10 neurons involved in memory or 1 million neurons, and no one knows even that. So even thinking about what the algorithm is used to memorize it is difficult to imagine. But in a broader sense, in some sense, AI tries to speculate on what the biggest functionalities are. And I suppose one comment is that there's a lot of discussion on these supervised learning deep nets, which which are kind of have been studied for a long time. They're reasonably well understood. They work amazingly well.
Can you explain for people who may not know what supervised
Well, yeah, okay.
is?
So the main point of supervised learning is that you, is that you train something to be able to do one function very well. So you may train a net to distinguish pictures from the web which have elephants and those which don't have elephants. And so with lots of data, lots of computation, good algorithms, you can do amazingly well. But the drawback is, almost by definition, is that although this net will know a lot about elephants, in the sense of being able to recognize a picture of one, it will know nothing else about elephants. You can't query it about elephants. And so that's very different from how we think. So we go to college, we learn lots of stuff, and when we learn stuff, we don't know what purpose we're going to use it for. So we have lots of information which we can collate by some sort of reasoning. So I think the area of future research is how to combine the supervised learning, which is extremely powerful, with more of a reasoning capability. And in some sense, of course, many practitioners have already got tip of this iceberg. So anyone who tries to combine many different nets, trains lots of different nets to different components of your problem, they're kind of approaching this more generic problem.
Yeah, and just another thought on this. One of the things I'm really intrigued by is the dynamics of the interaction, right? So the examples you saw here today were, in a laboratory, right, or in a clinic where we're doing one kind of task, but think of using these devices in your everyday life. And as you interact with your environment using these neural interfaces, if there's a potential for the algorithms to learn and for you to learn, and you combine those together, I mean, I think that's really where the richness of how AI will blossom and how our neural circuits will also kind of blossom in that way. So it's going to be really interesting and fascinating to see how people actually use these technologies in the future.
And how easy is the training right now? Like when Google or Facebook builds one of these deep learning algorithms, like you mentioned, it's a lot of training, it's a lot of compute power. So how do you push past that to make it easier and faster?
Yeah. Well, often you can, there's a trade-off. So with much less training, you can do maybe almost as well. So there's a trade-off which has to be examined. So if you have a certain amount of budget on your computing time, see what the best you can do with that.
Is it really a question of how much data you have, or is it the computing power? Where is the roadblock?
Well, in general, the more data you have, the more accurate your predictor will be, and the more computation time it'll take. But you can make compromises, and that's what we have to do.
I'd like to open it up for questions. Anybody?
Introduce yourself. Hi, Mark Bonchek with Shift Thinking. I'm curious, as you've been exploring whether it's neural interface, artificial intelligence, I imagine you're learning more and more about the brain, and kind of the mysteries are starting to get cleared up. Has that had you feel kind of more in awe of the brain, or kind of less because now we go, that's how it works? All right, not a big deal.
Yeah, for me, it's more in awe of the brain because we're learning about functions that we didn't even know about. And just to give you a concrete touch point on that, there's a lot of theory for, let's say, where memory is in the brain, right? There's this little structure called the hippocampus that is, again, years of work has gone into studying what it does. But now we're seeing that memory is, very much distributed throughout the brain. And, I don't think that we would have learned that unless we would have had the capabilities of designing direct neural interfaces and using them in the therapeutic way that we are today. So, the horizons for me are only expanding.
Yeah, I mean, for me as a more theoretical person, I have to assume that the principles behind how the brain works, which are somehow simple design principles. I mean, just from the evolutionary argument that cortex has exploded, and getting more cortex seems to be good for you. So there must be some very generic principles for understanding at least certain aspects of cortex. So I think some of the answers, in the end, I hope, will be Yeah. Is this only this?
Yeah, and we've seen, even amongst individuals, there are some core principles for how the neurons fire with respect to certain situations. So yeah, there's a foundation, I think, that we can build upon there.
Jody Westby. I'm thinking of our veterans and how can this work be used for phantom limb pain and for post-traumatic stress syndrome. I think of the veterans and I think of all the civilians who are being harmed in all these war zones. Is this something that could be used to help this?
Yeah, fantastic question. So one of the missions that I had when I came to DARPA was to try to restore functionality to people, military personnel, who have paid the ultimate price in service of our country. And again, the examples that I showed you here, even just movement, sensation, and memory, we are trying to develop those technologies so we'll have real therapies for those individuals. But getting to the point of other functions like PTSD and things like that, we are trying to deepen our understanding of the cognitive functions of the brain. And as we get those deeper understandings, I think we'll be able to address more medical conditions than the ones that we're initially starting our work in. So yes, this technology could absolutely help our military personnel.
It seems like there's a fundamental difficulty when it comes to inserting things in our brains over a vast scale, right? You kind of have to open the whole thing up. So how does DARPA look at that pretty substantial issue?
Yeah, another great question. So in all the examples that you saw here today, the people that volunteered to do this had to have a brain surgery, right? But if we think about neurotechnology in the future, let's say if any of us wanted to use neurotechnology, we need a better way of being able to sense those neural signals. And quite frankly, there's a biophysics problem with trying to access those kinds of signals. It's extremely tough. So if there's a challenge that I could put out to the scientific or industrial community is how do we develop the next generation neural interface that solves this particular problem? I'm completely fascinated by that and have been thinking about it for a really long time.
One of the things we know about memory formation and storage is that with each retrieval, you change the memory, and it's a living thing. When you're looking to build something like that that interacts with a human brain, how do you take that into account? How does that adjust your work?
It's great that you asked this question because you're getting down to the dynamics of how your brain changes over time, right? And speaking to one of the points that Leslie made here is that traditional, let's say, supervised learning approaches where we train an algorithm and then the parameters of that algorithm are fixed for all time after that, obviously that will not work in the long run for building neurotechnologies for everyday life. So we've got teams of scientists that are trying to figure out how are we going to adapt these systems as the neural circuits in your brain also change, right? And that really comes to the point of how do we build co-adaptive technology, right? I mean, think of an AI that adapts with you as you're using it. And for the brain, this is still an open research question that people are working on.
Well, one of the things that has people excited in the AI community is this idea of reinforcement learning. Yeah. So how does that fit into the work that you guys are doing?
Yeah, so reinforcement learning states the problem that the reward signal comes later on. It's not so immediate as in supervised learning, but to effectively do it, in my view, you have to get as much as you can from supervised learning. So there's no free lunch. So if you play a game and you're only told whether you win or lose 60 moves away, you've got no other information, it's pretty hard to figure out what to do. And this is the ideal of reinforcement learning. So I think so supervised learning is very powerful, and whatever you do, you seem to have to try to force that into the picture.
So a number of years ago, we actually developed some algorithms that seeded the decoders with supervised learning approach, and then we employed reinforcement learning in order to adapt the systems over time. And again, it's a very kind of simple idea that if you produce a neural activation that leads to a success of the task that you're trying to perform, then increase the weights of the model to reinforce that behavior. And conversely, let's say you produce a neural activation that does not help you, then kind of penalize the algorithm to not do that again. So again, I think fundamentally that idea could be used in the future for using these kinds of neural interface systems for long, extended periods of time that kind of adapt and grow with you, through experience. So again, it's another, I think, emerging area of opportunity.
What do you in your think are the final frontiers or the biggest challenges or things that have been most surprising to tackle and addressing all of them?
Yeah. So the use cases for how people would use it in their everyday life, to me, that's a huge frontier. As I started off by saying, is we're really just opening the door to what is possible, but nobody has written the story for where neurotechnology will appear in everyday life. And that's something that we're thinking about every single day, right? And we're trying to think about what's going to be our next vision, our next program that we may put out to the community to say, all right, let's start to define that. Let's start to say, what is this next area that we're going to be working in? So it remains to be seen.
We have time for one last question. Anybody? Go.
Thank you. So the kind of machine learning and deep learning technology that you're talking about, the tasks that you're doing, requires a fundamentally different computing way. Do you think you are limited by what's out there in computing today, or do you think you are at the same time looking at quantum computing and advancing there, and how far are we?
Yeah. I know we only have about a minute left. In the early days of doing this, we were limited by computing power to handle the volume of data that was coming out of the brain. Today, that's not necessarily the case. We've got enough processing power and speed in order to do a lot of the things that you saw here today. But again, as we expand the number of functions that a person performs with these neural interfaces, then that may be a place where the algorithms need to become much more sophisticated. The granularity of the algorithms may be much more sophisticated, or even the biophysics, the properties that we utilize in order to generate those functions may be very, very different. So there may be that bottleneck in the future, but again, it's something that I think that we need to explore.
Okay, thank you guys.
All right, thank you.